Assalamu alaikum, dear students. We're back with another video lesson. In the previous video lesson, we were talking about the two conditions of equilibrium. And the two conditions of equilibrium are, the first one, we can say for translational equilibrium, the net force must be zero, which means the forces that are upward must be equal to the forces that are downward here. And then if we have forces from the side, the forces that are to the right must be equal in magnitude and opposite to the forces that are to the left, let's say. And then the second condition was rotational equilibrium. For an object to be at rotational equilibrium, we said the net torque must be zero, which means that if the object is rotating, or if the object even at rest, let's say, the torques that are clockwise must be equal in magnitude and opposite in direction to the torques that are counterclockwise here. We solved some questions and we left some others, and we stopped right at this point here. All right, 3 or practice 3b, what does it say? It says a 400 Newton child and a 300 Newton child sit on either ends of a 2-meter long seesaw. So the first part of the question says, where along the seesaw should the pivot be placed to ensure rotational equilibrium? All right, so because it says rotational equilibrium, then the first thing that you have to begin with is using the net torque at this point here. Okay, so let's draw or construct the diagram and see how we can solve this question together. Okay, so this is what we have. This is the seesaw, we can say. Remember, there are two children. One of them has a weight of 400 Newton. So you can write it down here, 400. The other one is 300 Newton. Okay, and then it says sits on either ends of a 2-meter long seesaw. So the length of this seesaw is 2 meter long here. The question says, where along the seesaw should the pivot be placed to ensure rotational equilibrium? So let's say this is a pivot here, that this pivot is movable. Where do you have to put this pivot so that this seesaw will be in rotational equilibrium? And don't forget, because we've mentioned before, the person or the side that is heavier or the axis of rotation must always be closer to the side that is heavier. So this cannot be right at the center because this side is heavier. So it has to be moved closer to this side. But what distance exactly, we don't know. So how do we solve this one at this point here? So let's just solve together here. So that is what we have. Okay. The only thing that we know is, we know that this distance is 2 meters, but do we know what are the distances from each side? The answer is no. And let me tell you something that you've studied before. Let's say this line is 2 meters long that you've studied here. If I cut one part of this line here and call it distance, can you tell me what is the remaining distance for the other side here? Yes, can I just call it 2 minus d? So for example, if d is 0.5 or if this distance is 0.5, what is the remaining distance? Can I say this would be 1.5? Yes, but how do I know it is 1.5? Because you would say 2 minus 0.5, that would be 1.5. We're going to exactly use the same analogy here. We'll call this side distance here, even though we don't know what exactly is, but we'll just call it a distance. You can call it d1 if you want to. And then the other side, or the remaining distance that is left here, that is going to be 2 minus whatever this distance is. Now, all you have to do is just use rotational equilibrium, and that'll be it. So we can say the torque that is let's start with this one here. Net torque must equal to 0. So at that point here, we can say the torque that is counterclockwise must equal or must be equal in magnitude and opposite to the torque that is clockwise. At this point here, we have the force. You can call it F1 D1, F2 D2, doesn't matter. So let's just call it F1 D1, and then the other side here, let's just call it F2 D2 here. Okay, now F1, we have 400 Newton, and then the distance, we just call it distance here, and then the other side, it is 300 Newton times, what is distance 2? Instead of that distance 2, we can just say 2 minus distance here. Now, all you have to do, just solve this one here. First of all, how about you could multiply this 300 into the bracket here, but there's something even easier. You can get rid of this 300 Newton real quick by dividing both sides by 300. 300. This 2 cancels out. 400 divided by 300, that is 1.33. Okay, let's just say 1.3 here. At this point, distance, it is equal to 2 minus distance here. Remember, the value for this distance is 1. Now, distance and distance has to be on one side here. So we'll just move this distance to this side. That'll be 1.3 distance plus this is 1 distance. Don't forget it is equal to 2. Now 1.3 plus 1, that is 2.3 distance. That is equal to 2. Now how do you find the distance? You could just divide this 2 by 2.3 or divide both sides by 2.3. Whatever you do, that is totally fine. 2 divided by 2.3. So the answer for this one, it is going to be by rounding, it is 0.86 at this point here, and that is going to be in meter. But don't forget, that is not the whole answer yet, because now you have to find this one here. So now we found this distance, which is 0.86 meter here. What about the distance for the other side here? It is going to be 2 minus 0.86, which is going to be 1.14 meter here. This question came in Wazari. You really have to be very careful. In Wazari, they might say 0.8, after you find the distance D here, you might say, or the multiple choice might say 0.86 from 300 Newton, and that'll be incorrect. Remember, we said the heavier side must be closer to the axis of rotation, so the shorter distance must always be to the side that is heavier. Don't forget that. Now, in Wazari, like I said, they brought this question here, maybe, sometimes different numbers, of course, but if they say 0.86 meter from the 300, that'll be incorrect, because there's the smallest distance, or the smaller distance cannot be with a smaller force as well. Okay, what about 1.14 meter from 400? That is also incorrect. So it has to be the larger distance with a smaller force, so that it can make up for this, and then these two would be balanced. And this is how you can answer this question easily. All right, what is the second part of this question here? The second part says what? Suppose that a 225 Newton child sits on 0.2 meter from the 400 Newton child. Where must a 325 child sit to maintain a rotational equilibrium? Don't forget this. Now, that'll be the second part of this question. Let's bring this one back again. So now at this point, we can clean it up a little. Okay, so that is the same. Let's clean this one too. That is the same seesaw here now. Don't forget these distances. So that is the same seesaw. This is the 400 Newton child, we can say. And this is the 300 Newton child. We already found the axis of rotation. We said this distance, it is 0.86 meter. And then the other distance was 1.14 meter. Okay, now another child sits on the seesaw, but this child is sitting 0.2 meter from this 400. By the way, the weight of this child is, what is the weight of this child? The weight of this child is 225. And then where another child should sit on the other side of the seesaw, but the weight of this child is, what is the weight of the second child? It is 400 Newton. Where must a 325? 325 child sit to ensure rotational equilibrium. All right, so let's do this one again. So don't forget this. Because we've already found the other part, so we really don't have to do the whole thing here. Now, the only thing I redraw this one so that we can find this distance. Now, watch this very carefully. Now, we know that if the distance from the 400 Newton child to the axis of rotation is 0.86 or 86 meter, now this child is sitting just 0.2 meter away from this one. If this distance is 0.2, what is the remaining distance then? That'll be, can I say 0.86 minus 0.2? So the remaining distance between this child and the axis of rotation is going to be we can say 0.66. The reason why? Because now this distance minus 0.2, all right, that'll be this distance left here. This is the same as if you just take away this part from this. What is the remaining distance? That is 0.86. Now, Because the seesaw was previously balanced, so you really don't have to include this part right here. You don't have to include these parts now, right? So you can just remove these if you want to. Because now the only thing I redraw this one so that we can find the distance of this person or child from the axis of rotation using the other person. Now we have a force and a distance. A force on this distance is unknown. You can call it whatever the distance is. You could just find it here. So now using the net torque, which is equal to 0, then the torque that is counterclockwise must equal to the torque that is clockwise, which you already know that. For the counterclockwise, this is counterclockwise. It doesn't matter which one you make them, clockwise or counterclockwise, doesn't matter, as long as you do the calculation correctly. So 225 multiplied by 0.66, that is equal to 325. By the way, this is force times the distance, don't forget. Force times the distance, don't forget. All right, so 325 times the distance, which is unknown here. So multiply this, divide by 325, you can find the distance, which I believe it is, let's use a calculator, see what it is. I think it is 0.5. So 225 times 0.66 divided by 325. The answer is going to be 0.456. You can say 0.5 by rounding here. Yes, 0.5 by rounding meter. That is how far this child should sit to ensure rotational equilibrium. And that is the answer to that question. So we're done with this question too. Now, if you remember, this is one of the Wazadi questions that it came before. And by the way, this question came in 2025 as well. So make sure you know how to do this one very well. Okay, now, if you remember, I left one of the questions in page number 79. I think it is a perfect time to go back to that question and solve that question here. And I can tell you perhaps now why we left that question. So I think we should, where's the keyboard? Oh, it's supposed to be here. Okay, let's bring it back. Page number 79. It's not writing. Okay, 79. This question that I'm talking about, if you remember. Okay. What does it say? And let me read the question first. It says what? A wooden bucket filled with water. And we had a similar question like this, by the way, but there is one extra part which I left it out. That is why. There's another reason. It says a wooden bucket filled with water has a mass of 75 kilograms and it is attached to a rope that is wound around a cylinder with a radius of this much. And up to this point, we had a question similar to this, so there's nothing special about this. But the second part is this. It says a crank with a turning radius of 0.25 meters attached to the end of the cylinder. What is the minimum force directed perpendicular to the crank handle that is required to raise the bucket at a constant speed? The reason why, another reason why I left it, was the main reason was this one here, because it says what is the reason that what is the force that is required to raise the bucket at a constant speed? When it says at a constant speed, we know that if something has a constant speed, in that case, of course, that means the object must be at rotational equilibrium here, because we said if the speed is constant, omega initial, or even if it is constant speed here, but because it is rotating, so omega initial must be equal to omega final. If that is the case, the angular acceleration is 0, so we can say the net torque is 0. If the net torque is 0, that means the torque that is counterclockwise must be equal in magnitude and opposite to the torque that is clockwise. I hope you can see that. If not, that's totally fine. So now let's bring the whiteboard and solve this one together too. Okay, so getting back to this one. Let's erase this one first. Let me perhaps maybe draw a diagram for what we have. So this is, we can say the cylinder here. This is the center of the cylinder. No, it's too much. and this is the bucket of water, has a 75 kilogram. Remember, this is the mass. This mass can be turned to Fg, which is equal to mass times gravitational acceleration here, and this is the radius. And then on the other side here, this is the crank handle where you just rotate this. If I help you with this, you can see that. This is the radius of this crank handle. Let's make this one smaller a little bit. Okay, watch this. So this the cylinder that this rope is, let's say, curl around. So once you rotate this handle here, it can lift up this bucket of water here. So this is where you apply the force. But don't forget, this crank handle has a radius too. So don't forget, that'll be a force. And this radius here, both, it produces a turning effect. So that'll be a torque in here. This water, which is, or the water and the rope also produce a torque around this cylinder as well here. So now this would be, the mass we said it is 70. Let's just make this one bigger. The mass was 75 kilogram. The radius of this cylinder, it is 0.075 meter. And then this, the force that is applied to the crank handle, it is unknown here, but the radius of the crank is 0.25 meter here. Okay, so what is the torque here? Once again, now at this point you will have to use the rotational equilibrium. And then the reason why rotational equilibrium, because the question says in order to raise the bucket at a constant speed, if the rotational speed is constant, that means the net torque is zero. If the net torque is zero, that means the torque that is clockwise must be equal in magnitude and opposite to the torque that is counterclockwise. So if the net is zero, we can say the torque that is counterclockwise must equal to the torque that is clockwise. At this point, it doesn't matter which one is clockwise or counter. So this one, force times distance, must equal to, you can call it F1 d1, and then F2 times d2 here. One of them for the bucket, and then the other one you can say for the crank handle or whatever. Doesn't matter. Okay, like these names, you can name them whatever you want to. But instead of the force, we have a mass. So we know that mass times gravitational acceleration, that'll be the force. Instead of the distance, we have the radius, right? That is first. And then on the other side here, we don't have the force. And then instead of the distance, you can call it radius 2 if you want to. And this is radius 1. So now, the mass that we have, it is 75 times 9.81. That is the force. Multiplied by the radius, which is 0.075. It is equal to F2 times the radius 2, which is 0.25. Now, there is another question. Sometimes the question asks, Mr. How do I know which radius is for which? And that is pretty easy as well. Let me tell you this, what is the force equal to? Then I can tell you how we can do that as well. Now, you could just move this one under this, and you can find F2. So F2, it is equal to whatever this divided by 0.25. So let's do this. 75 times 9.81 times 0.075 divided by 0.25. The answer is going to be 220.7. 220.7, which is about, you can say 221 if you want to. That is going to be in Newton. This is how much force must be applied by the crank handle so that you can rotate this one, and that, of course, lifts up the water at a constant speed. Now, let's go back to this one. How do I know which one or which radius is for which? Okay, so if you look at this point here, the first one says, what does it say? It says a wooden bucket. Perhaps we need to get this one back and then get rid of this one. Okay, now take a look at what we have. All right, now it is writing. It says a wooden bucket filled with water. So this is the mass of the bucket of water. It says attached to a rope that is wound around a cylinder with a radius of this much. So this radius, it is for the cylinder, which is wound around the mass, which is right at this point. So this is the mass. So this would be the radius of the cylinder. And then there is a full stop, as you can see here. A crank with a turning radius. So it says a crank with a turning radius of this much. So the second radius is for the crank, which is at this point right here. So I believe this is how easily you can differentiate between which one is for which, and that'll be it. Okay, now going back to the page where we left, we have to exit this one. It was 95, I guess. It's not writing again. These are really not helping. Oh, that is finally okay. So that was the page where we left. Don't forget to practice this question, which is also very important. Now, the last question that we have, you can say, for the rotational equilibrium at this point is, or let's say levers, and that is this question here. This question might take a little bit longer than usual, but nothing complicated. Just stay with me and make sure you write your notes, and then hopefully, inshallah, everything will be very easy. So what do we have? It says a 0.1 kilogram meter stick. Don't forget, whenever it says a meter stick, that means there is a stick which is 1 meter. And also, even if it is not mentioned as uniform, because meter sticks are always uniform. So the center of mass of that meter stick will always be right at the center. But there is one thing you need to be aware of. Instead of giving you the weight of the meter stick, they gave you the mass of the meter stick. Okay. Which is 1 meter long, by the way. I've added this one so that you know what it is. Otherwise, in questions, you will not be given this, what is written in bracket. It is supported at 40 centimeter mark by a string which is attached to the ceiling. How about if we just reconstruct the diagram, because the diagram for this question will not be given, but you can always easily draw the diagram for yourself. Okay, so let's draw the diagram, and then after that, solve this question together. So here's a meter stick that we have. When it says, when we say 1 meter stick, that means it is 100 centimeter long. Here's the 0 centimeter, and that is 100, we can say, centimeter, and that'll be for this, for the meter stick. And then we know that the center of mass, it is always right at the center, and this center would be at the 50 centimeter mark. It says the mass of this meter stick, it is 0.1 kilogram. That is first. It says supported at 40 centimeter mark. Now, since you mentioned, or you made this 0 and then the other one is 100, now 40 centimeter has to be at the side which is less than 50. Don't forget, we said this is the center, and the center it is 50 centimeter from 0 here. That 50 centimeter will be the same as 0.5, you know that. But it says supported at 40 centimeter. If that is the case, then you'll have to draw it here. All right, so let's just make this one 50. I can write it here. Okay, and then this is 40 centimeter. That is where it is supported. These are in centimeter, don't forget yet. Okay, next it says a 40 centimeter mark by a string that is attached to the ceiling. And then 0.7 kilogram mass hangs vertically from the 5 centimeter mark. Where's 5 centimeter mark? We can say 5 centimeter mark is somewhere right here. There is a mass attached to this point. This mass is 0.7 kilogram. At where? At 0.5 centimeter mark, let's say. Let's not convert it so quickly. 5 centimeter mark. The next thing says, a mass is attached. So do we know how much mass is attached to this? The answer is no. Let's bring this one back. I should have pinned to the screen here. Okay. Now it says a mass is attached to the screen. Do we know how much mass is attached? To the screen, that's new. All right, it says a mass is attached. Do we know how much mass is attached? The answer is no. So there is a mass, which is unknown here. That is first. It says also, the second thing, it says somewhere. That means we don't even know the distance here as well. So the distance for that mass is also unknown. So now at this point, we have two unknowns. The mass is unknown, and the distance where the mass is attached is also unknown. That is on the meter stick to keep it in horizontal and, let's say, horizontal, and in both the rotational and translational equilibrium. So this meter stick is in both the rotational and translational equilibrium. If the force applied by the string attached to the meter stick is, how much force is this? It is 19.6 Newton, determine the following. So this, we can say it is 19.6 Newton here. Determine the following. What is the first requirement that they want? It says the value of the unknown mass. Okay, so now I think it is time to solve this question together. The first thing that we're required to know is we have to find the value of the unknown mass. Let's just zoom out this one here a little bit. Okay, so now we know a mass is attached somewhere. but we don't know where exactly. Okay, so let's just say the mass is attached anywhere here. Let's just write a mass in here. But what is this mass? We don't know. Where is it? Again, we don't know here. Now, let me remind you one thing that we've said. Do you remember we said you can start using, or 99% of the questions can be solved by using the net torque equations first. So 99% of the questions can be solved using this one here, which we can say the torque that is counterclockwise equal to the torque that is clockwise. This is one of the questions, or one of the 1% remaining or left, that it cannot be solved by starting to use this equation first. Do you know why? Because in order to find torque, we need both force and distance, and we don't have them. Clearly, there's a mass. You can convert that or change that to a force, but we don't have the mass and we don't have the distance, so I cannot have two unknowns in an equation. So what do? I'll start with the second equation first here, which in this case, F net, it is equal to, if that is equal to 0, then I can say the forces that are upward must equal to the forces that are downward here. I don't have any forces from the side, so that is a relief at this point here. But look, what are the forces that are acting downward? Instead of the forces, I have masses, but we do know that every mass, it can be converted into a force by using mg, right? And then these as well here. So now I can say, how many forces are upward? There's only one force that is upward, which is 19 point, about if we just call it F tangent at this point. F tangent, it is upward, it is equal to how many forces that are downward? 3. That is, we can say F1 plus F2 plus F3. You can call this one M1, you can call this one M2, and you can call this one M3. And you might say, how do you know it is a force? How do you know it is downward? Of course, if it is attached to the ruler, it is hanged, which is clearly it is downward. All right, so that is 19.6. It is equal to this force in here. Instead of this force, can I just call it mg, m1g plus m2g plus m3g, right? Now you can see that there is g, which is a common factor between each one of those. So can I take g as a common factor? Yes. So 19.6, it is equal to, let's bring g forward, that is m1 plus m2 plus m3. Do you agree? Now, how about if I just divide both sides by g? We know that the value for g is 9.81, right? That is g, then these two cancel out. 19.6 divided by 9.81. How about we just do this one? 19.6 divided by 9.81. The answer is going to be 1.99, which is about 2, I can say. Let's say 2 by rounding. And then what else do we have on the other side? M1, it is 0.7 plus M2 is 0.1 plus M3, which is unknown here. 0.7 and 0.1, that is 0.8. If we move to the other side, 2 minus 0.8, that is going to be 1.2 by rounding, and that is M3. So we can say M3, it is equal to 1.2. So M3, it is about 1.2 kilogram. Now we found the mass of M3. Now we can say this is about 1.2 kilogram. All right, then that is the first requirement. Find the mass or find the unknown mass, which is obviously now it is 1.2 kilogram. Once again, we could have not used the net torque to do this one because we did not have the mass and we did not have the distance either. Now, what is the second part of the question? Says where along this let's say meter stick, this mass should be attached. Let's go back to the question and see what it is. It says where, the second part says at the point, or determine the point where the mass attached to the stick. That'll be the second part of the question here. Where along this mass, okay, so let's do this one again. What distance this mass should be attached here? So this time the distance is unknown. But if the distance is unknown, can I find the distance? Yes. By what equation? By using the second equation, or rotational equilibrium. Now, net torque must be 0, which we can say the torque that is counterclockwise must equal to the torque that is clockwise. Once again, we'll have to use one of these points as the axis of rotation. Can I use this point as the axis of rotation? Absolutely yes. Can I use this point as the axis of rotation? Yes, but you have to be careful. Then whenever or once you find the distance, you'll always have to say whatever the mark that you find, you'll have to compare it to 0 at this point so that you can find it here. And then you can choose any other points as the axis of rotation as long as that point allows you to find this distance right here. Okay, so now we're just going to use this point, 0 point, as the axis of rotation. If that is the case, this force is producing a counterclockwise torque. So this is positive, and these will be clockwise torques here, which are negative. So in that case here, we can say the torque that is counterclockwise, we can say force times distance here. That is tangent because suspended. Then the other, it is equal to the other forces here, F1, F2, and F3 here. So F1 times D1 we can say plus F2 times D2 plus F3 times D3. You can say this D3 now, it is unknown, but be careful here. We're given the masses, not the forces. This is 19.6 times, how far is this point from the axis of rotation? 40 centimeter, and that is 0.4 meter. Let's just write 0.4. It is equal to. Now, the first force here, instead of the force, we have, remember, the mass, but mass times gravitational acceleration, that would give us Fg here. So we can say 0.7 times 9.81 times, how far is this mass from the axis? 5 centimeter. Convert to meter, 0.05 meter. And then that is the first one. Plus the second force, it is 0.1 kilogram times 9.81. Now this is from the center of the meter stick, which is how far is the center from the 0 mark? That is 50 centimeter, which is 0.5 meter here. And then plus F3. We have the mass, which is 1.2 times 9.81 times how far is this mass from the axis of rotation? That is unknown here. You can call it D3. Now, all you have to do, just add these two together, okay, multiply them, add them together, and then you will have to move them. Add these two together, and then you will have to move to this side and then subtract it from the answer to this one. So let's do this one. 19.6 minus, we could have just saved some time, we could have looked at the answer here. But I'll just do it. 19.6 times 0.4. The answer is going to be 7.84. And here's what I'm going to do. I'll multiply those, and then I'll just bring them here right away. The first one, it is 0.7 times 9.81 times 0.05. It is 0.34335, whatever, plus the second one, it is going to be 0.1 times 9.81 times 0.5, and then the total is 0.83385 or whatever. So we'll just bring them to this side here, minus 0.833. Okay, 83 for now. That is equal to, what is this equal to? 1.2 times 9.81. That is equal to 11.77. We can say 11.8 by rounding. 11.8 by rounding D3 here. So how do you find D3? Just subtract this two. 7.84 minus 0.83 is equal to this much divided by 11.8, because whatever the answer is, you'll just divide by 11.8, then the answer is going to be so D3, it is equal to 0.594 or whatever. Can we round it up to, that is in meter, by the way. Can we round it up and say it is 0.6 meter? Yes, but that is in meter. What if you see the choices or the multiple choices were in centimeter? That is the same as saying 60 centimeter mark. So this mass has to be attached to the 60 centimeter mark from the axis of rotation. So this distance now, it has to be 60 centimeter. This is how you can do that. Okay, the steps might be a little bit long, but if you do that like each step at a time, then it's nothing that complicated, and I hope you understood this one. All right, so we can say that was one of the last questions. By the way, this question came in Uzari too this year, so but it was a little bit different, so we're gonna solve that question too and see how it was, so hopefully you can benefit from that as well. And that is how we did it. I've tried to make it as easy as possible here as well. Okay, so this is the diagram. The first thing you'll have to find the mass, which is about 1.2 kilogram. Then the second part, you will have to use the network to find the distance, which is 0.59 meter. We said you can round it up to 0.6, and that is how far this mass it is from the axis of rotation. Now let's see the Uzari question regarding this one and see how it was. Or the question that it came. By the way, it was a good question too, and that is this question here. What does it say? It says, it was one of the question, by the way. It says a meter stick, it is supported at, 50 centimeter mark by a string attached to the ceiling. A 0.9 kilogram mass hangs vertically from the 80 centimeter mark. Let's just convert this one to a drawing. Okay, so let's clean this a bit bigger. Let's get rid of this one for now since we don't need it. Okay. All right, so let's move this one a little bit. Here's the meter stick. Says a meter stick. Remember, when it says meter stick, that means the length of this meter stick, it is 100 centimeter. You do know that. That is 0. And let's say this is 100 centimeter. All right, the next thing says it is supported at 50 centimeter marked by a string attached to the ceiling. So right at the center, it is supported at 50 centimeter mark. So this distance, it is 50 centimeter. That is first. Second says, a 0.9 kilogram mass hangs vertically from the 80 centimeter mark. So let's say this is 100 and this is 80 centimeter. That is 0.9 kilogram. So this distance now, okay, we could just say this distance, it is 0.80 80 centimeter, which is 0.8 meter, we can say. All right, what is next? It says, and 0.8 kilogram from mass is attached from the 20 centimeter mark from the meter stick. So from the 20 centimeter mark, there is another mass attached, which is 0.3 kilogram. So once again, this distance is 20, since we kept all this in centimeter, so this is 80 centimeter. Okay, and this is 20 centimeter. What is the question here? It says, find the location of a point that 0.3 kilogram mass should be attached to the stick to keep it in a state of rotational and translational equilibrium. So we have to find a point, okay? Find the location of a point where 0.3 kilogram, where's the other one here? 0.8 from, this is 0.8, my bad. This is 0.8 kilogram that is attached from the 20 centimeter mark. So find the location of a point that 0.3 kilogram mass should be attached to the stick. So now we know that if this is where the meter stick is supported here, you can clearly see that this side is heavier than this side here. And by the way, if it is supported at this point here, we're going to use this point as the axis of rotation. Why should or cannot use this point as the axis of rotation? Because I don't have the upward force. If I had the upward force, then I could have easily used this point as the axis of rotation. But because I don't have the force at this point here, I cannot use this point here, because then it would be two unknowns. And if it is two unknowns, I cannot do that there. So we'll consider this point as the axis of rotation. If that is the case, how far is this 0.8 from this? You can see that the whole thing is 50. So if this side is 20, then this is going to be 30 centimeter. You might wonder, why am I doing this? This is from 80 centimeters. So how far is 80 from 50? That is also 30 centimeter. Now, the reason why I'm going to add the mass to this side is because of this. I have 0.0 kilogram, which is 30 centimeter far from the axis. And then there is 0.8 kilogram, which is 30 meter far from this side. So the mass, or the unknown mass, has to be attached to this side here so that it can ensure rotational equilibrium. So let's say this is the 0.3 kilogram mass, but I don't know what distance is it from the axis of rotation here. And at this point here, you have to be a little bit careful, because eventually we'll have to consider this distance from the axis of rotation. Okay. Now, so once again, what can I do to find this one here? So normally we'll say the forces that produce counterclockwise must equal to the forces that the torques that are clockwise must be equal in magnitude and opposite to the torques that are counterclockwise. So we'll say the net torque is 0, and that if that is the case, the torques that are counterclockwise must equal to the torques that are clockwise here. If this is the axis of rotation, so these two produce both counterclockwise, and this is clockwise. Okay, so at this point here, we have two force, you can call it F1 D1 plus F2 D2 must equal to F3, let's say D3 here. Okay, you don't need brackets for the other side here. All right, now what is the first force in here? That is 0.8 kilogram. Once again, we don't have the forces, we have mass, so 0.8 times 9.81. By the way, I can take gravitational acceleration as common factor, so let's just use this one. M1 D1 plus M2 G D2. It is equal to M3 times G times D3. So you can see here we have G on both sides here. I can take a common factor. That is going to be M1 D1 plus M2 D2. These are times G. That is equal to G M3 D3 here. These two cancel out. What is the first mass? 0.8 times. How far is it from the axis of rotation? 0.3 meter plus. What is the second mass? It is 0.3. But do we know the distance? No. So let's just call it D2. It is equal to, what is the third mass? It is 0.9 kilogram times 0.3 again. So there's only one unknown here. You can easily find it here. 0.8 times 3. Okay. 0.8 times 0.3. The answer is going to be 0.24 plus 0.3 D2. It is equal to 0.9 times this one, that is 0.27. Okay, now how do you find D2 here? Move 0.24 to the other side. We can say 0.3 D2, that is equal to 0.27 minus 0.24. 0.3 D2, it is equal to 0.27 minus 0.24. That is equal to, I don't want to give any wrong answers actually. It is 0.03. And then D2, it is equal to 0.03 divided by 0.3. And what is the answer equal to? 0.03 divided by 0.3. The answer is going to be 0.1. Don't forget. D2 it is equal to 0.1 meter. But don't forget, if I convert this one, that is 10 centimeter. But write a note for yourself. This D2, 10 centimeter, is far from the axis of rotation, which is at 50 centimeter mark. But where exactly along the meter stick should this meter ruler be attached to? So now if I just watch this one, I'll just erase the whole thing that I don't need to. This D3, like how far is it from the 50 centimeter mark? It is just 10 centimeter. All right, if it is 10 centimeter far from the 50 centimeter mark, how far is it from the 0 mark? It is 40 centimeter. If not, you could just say this, the whole distance is 50. So 50 minus 10, that is 40, which is the same thing as well. But I think it will be easier. This is the 50 centimeter mark. If it is 10 centimeter from 50, so what is the distance from this point to the 0? That is 40 centimeter mark, and that is the correct answer. So let's get back to the options and see which option is this. It's a little bit was time consuming, but of course I think it's worth it. So that is option C. You can see that, but I'm trying to get this one back so that we can highlight this or circle this one here. So once again, that is the answer. Once again, make sure you know how to do this one here. And the rest of the questions, of course, you can give it a try yourself, which I have no doubt you could easily solve them. All right, let's see. I think we spent a lot of time on these questions, but I'm sure worth it, guys. All right, now we have a few more questions regarding this. Some of the questions that we've solved. Let's answer a few questions here, and then after that, I'll solve this question too, because this one is also it has a great idea in this one too. It says a solid cylinder rotating around a fixed axis, and the net external torque is equal to 0. Make sure you underline the keywords here. It is rotating, that is first. Okay. I think we'll have to get the other one back and see what is wrong at this point. Why we're not getting this. Okay, so great. All right, so it says rotating around a fixed axis and the net external torque acting on the object is 0. If the net torque is 0, then what can we say? It is angular velocity is changing. If the net torque is 0, can we say that? It says it is angular acceleration of a cylinder is not equal to 0. Okay, it is angular acceleration of a cylinder is not equal to 0. It has no rotational equilibrium, and it is none of them. Which one of these do you think it is at this point? Remember, it is rotating around a fixed axis and the net external torque acting on it is 0. It is angular velocity is changing. Is it true? If the net torque is 0, is the angular velocity changing? The answer is no. All right. It is angular acceleration is not equal to 0. That is also not true. Because if the net torque is 0, the angular acceleration is also 0 as well. Because later we'll have this equation, the net torque is equal to moment of inertia times angular acceleration. If the net is 0, clearly the angular acceleration must be 0 as well. C says it has no rotational equilibrium. Well, if the net is 0, then it must be out of rotational equilibrium. So in this case, we can say it is none of them here. Okay, now what about the next question here? It says identify which condition of equilibrium hold for a bicycle wheel rolling along a level highway at a constant speed. We said if it is a constant speed, then is it just translational, rotational, or both translational and rotational? It is both translational and rotational because it says constant speed and a level highway. So, and that is both here. The question that I wanted to solve for you guys is this one here. It says two forces equal in magnitude, and that is F1, F2 acting on the bar, as in the adjacent figure. The net torque acting on the bar is this much. Find the distance L between the two forces here. The idea in this question, which is also very interesting to know that, if you remember previously, we were always saying the torque that is clockwise equal to the torque that is counterclockwise, and we were saying the net torque was 0. But remember, the net torque is only 0 when the object is at rotational equilibrium. But here it says there is a net torque. If there is a net torque, in other words, if the net torque is not 0, we cannot say the torque that is clockwise and counterclockwise are equal in magnitude and opposite in direction. So you really have to be careful regarding that. So let's do this one. How about first, let's redraw the diagram and then see what is given and what is unknown. Then we'll just expand the whiteboard here. So the first one, this is the axis of rotation. oops. Let's get back to this one. This is the axis of rotation. There's the first force, which is F2, and then this is F1. Each one of these forces 20 Newton, 20 Newton. Okay, and then the distance between F2 and the axis of rotation is 3 meters. And then F1, it is unknown here. This distance, it is unknown here, but we can say the distance between F1 and F2, it is equal to L, this distance right here. And don't forget we have a net torque. What is the net torque? It is negative 12 Newton meter. Because it is negative, that means this beam here, or this bar, it is rotating clockwise, don't forget. So no longer I can write F net is equal to 0. Why? Because there is a net force in here. Well, if there is a net force, what can I say? I'll have to say the torque that is clockwise must plus the torque that is counterclockwise in here. Or you can say F1 or torque 1 plus torque 2 here, because we have two torques here. The net is negative. Negative what? Negative 12. So we're just going to write it down. Plus torque 1. What is torque 1? That is for the F1. Is this one clockwise or counterclockwise? This one is clockwise here. So we can say negative force times distance. And then plus torque 2, which is F2. This is counterclockwise, which is positive. So let's call this one F1 D1, F2 D2 at this point here. So once again, negative 12, it is equal to negative. What is F1? Each force is 20 times. But do we know this distance between F1 and the axis of rotation? The answer is no. But there is one thing we can do that. We can immediately say L, the distance equal to L plus 3, because that would be the distance from the axis of rotation to F3. But for now, it is easier if I just call it a distance now. For calculation, by the way, I'll just call it D1 here. And then plus F2, which is again 20 times 3 at this point here. All right, so negative 12, that is equal to negative 20 D1 plus 60. Because 20 times 2, that is 60. Now, all you have to do is numbers at one side and unknown at the other side in here. Okay, so how about let's just expand this one here and zoom out a little. All right, so now, once again, negative 12. How about if I just move this 60 to this side here? That is going to be negative 60, negative 200, 20 D1 here. So 12. Negative 12 and negative 60, that is negative 72, negative 20, D1 here. This negative and negative cancel out. So D1, was it D1 or D2? D1. So D1, it is equal to 72 divided by 20. That is 3.6 meter here. Now, but don't forget, the question says find the L, not the distance here. So how can I find this one here? Can I say D1 it is equal to now? D1 it is equal to 3 plus L, yes? I didn't want 3 plus L into the equation because that makes the calculation to be a little bit longer in that case. So now we found D1, that is 3.6, that is equal to 3 plus L. So can you find the L here? That is 3.6 minus, move this one to the other side, 3, it is equal to L. So now we can say 3.6 minus 3, that is 0.6 meter. And that is the answer for L here. So this L, or this distance, it is 0.6. That would be the distance between F1 and F2 here. So let's go back to the question and see which option is this. We can see that here. Of course, for more questions, you can join our channel. Of course, you can see a lot of questions over there. All right, inshallah, next session we'll talk about rotational dynamic. That is also a very interesting concept, which is also easy. We're done with lever arms and let's say those kind of questions. So hopefully the next one will be easier, which I believe it is way easier. So till then, keep practicing and I'll see you soon, inshallah. Assalamu alaikum wa rahmatullah.